Okay.
Recording. So no problem recording, right? Because you presented it already.
Yes.
Okay, so let me go to my notes here. There is a note here, start recording with exclamation points. I wonder why I always record. So it's a pleasure to have Professor Ferreira here today to talk to us. Professor Ferreira got a bachelor's in São Carlos, USP, in 2005, and his PhD also at USP São Carlos in 2011. He did 2 postdocs that I at least know of, 2012-13 at University of Basel in Switzerland. And 2013-14, he was a postdoc in São Carlos too at USP. And since 2014, he is a faculty at the Physics Institute in Uberlândia. And today he's going to talk to us about his developments of the codes, DFT2kp, effective KP models from ab-initio data. So, Professor Ferreira, thank you very much for accepting our invitation, and the microphone is yours.
Thank you, George, for inviting me to give a talk here. And okay, so I'm going to talk about this code DFT2kp that we have been developing for a while. The paper was published earlier this year in SciPost Physics Code Bases. It's a new journal. SciPost Physics has traditional physics, and the SciPost Physics Code Bases is focused on open source codes. So it's a very appropriate paper to this kind of stuff. The code is available at the GitLab repository if you want to try. And okay, so I'm gonna start just acknowledging my co-author. So this is the print screen of the paper with the title, and it was developed initially by João Vitor, who was a master's student in my group. He developed most of the code, the initial version of the code, and then he moved to do a PhD in São Paulo and didn't finish the code, but most of the code is his work, at least the first version. Augusto was a previous student here from the group. He helped us with the DFT calculation. Paulo, who I think is on the audience here, was our collaborator on the DFT and K.P theory and overall development of the code, and myself. Just one point that I want to show here is that Paulo was at Regensburg at the time, and now he's moving to Orlando as a professor, and we hope to keep nice collaborations in the near future. So before I start the talk itself, let me just tell you why DFT2kp. What I'm going to do here initially is just going to flash some titles of some relevant papers that uses structures or features that are similar to what we have here. And then later I'll move to the talk itself. So there's a bunch of papers who use K.P methods to calculate the G-factor spin-orbit couplings straight from DFT. I selected just a couple here. The literature is huge, okay? So this is an important one from Fabian's group and Dimitra. So in this paper, they calculate the spin-orbit couplings for K.P models straight from DFT calculations. Another one from Paulo and collaborators, Paulo and V. Chaves and collaborators, they calculate the exciton G-factors, again, from first principles, from DFT calculations, using methods of calculations that are very similar to the ones I'm going to present here. There are papers who fit K.P models to DFT data. So they run the DFT, they get the bands, and they run the K.P model separately, and they to find the parameters for the K.P model, they just try to fit both data together. So, for instance, Tesselin's group do a lot of papers on this fashion. So this is a K.P model, multi-band K.P model for perovskites. The focus here again is in the G-factor calculation. Third band K.P models for 3,5 compounds, gallium arsenide, for instance. 8 band K.P models for perovskites. K.P models for hexagonal germanium, a very recent paper from Guido Burkhardt group. I just want to tell you guys that it's a really, really hot topic with many different papers working on similar subjects. You can do also alloys with finite composition. So, for instance, for Wurtzite systems, there are recent papers for K.P alloys. This one is for diluted semiconductors on the 3,5 group with nitrogen, 10-band K.P models. For germanium alloys and for highly mismatched alloys. So there's a bunch of papers working on similar topics still nowadays. We here in Uberlândia have been working with similar topics as well, so I'm just going to show some here. In 2016, we did this topological non-symmorphic ribbons, and to get these results, we had the DFT calculation from Tomás group, and I did the K.P model for them, and to make the models match, I had to fit the data. Very similar here in this I had from 2018. I had to fit a K.P model to Tomás DFT calculations. More recently, with Carlos Egues, we did the Wurtzite model, K.P model for heterostructures to create quantum wells based on this K.P model. So it's a very rich literature on these subjects. And as I said, it's a hot topic. And what I mean by hot topic is that while João Vitor was developing the first version of the code, this paper came out in 2020. It was really in the beginning of his development. And what they did is exactly the same thing we did here. It's pretty much the same project, but they didn't provide an ab-initio code, open source code. So we kept developing it. And while our paper was with the referees, we saw this paper published pretty much together with ours, like a few months apart, where they also do pretty much the same kind of calculations with slightly differences in the methodology. Besides the K.P model, you know, there is also tight binding models from DFT. The famous ones are Vanien 90 and PowerFlow. They extract tight binding models from DFT calculations. So this was just an overview to show you that the literature is quite rich. I'm not going to go into the details of those papers. So for the talk today, I actually going to focus on our code from now on. So I'm going to start with an overview of K.P theory and the loading partitioning, which come together with K.P. I will not talk much about group theory, which is also necessary to learn the details here. I can do this some other time. And then I go to the DFT code, and to present the DFT code initially, I'm going to focus on examples, majorly on graphene, and I'm going to just flash some results for other materials. And at the end of the talk, I'm going to show some perspectives about what we are doing for the next version of the code. And if I have time, I'm going to open up the code and show you how it runs. Okay? So let's go. Let's start with a K.P overview. So this is just going to be like a really brief overview. If you want more details, you can check Von and Willotzing's book or Winkler's book. For group theory, Tinkham and Dresselhaus' book are the ones that we usually recommend. So, okay, K.P. So what do we want from K.P? For instance, if you have graphene, this is a traditional picture for the band structure of graphene going in the Brillouin zone from gamma to K, to N and back to gamma. So this is a DFT calculation with all the bands in here, and we don't want to describe all the bands. Within K.P theory, we want to describe just a small section of the Brillouin zone. In this case, is the Dirac cone that is composed by these E2 prime bands. You can think about the Dirac cone as these two bands. If you rotate in space, you get the Dirac cones here. Or if you want to work with gallium arsenide, for instance, this is the DFT bands for gallium arsenide. And in this case, we want to describe either the conduction bands, which is parabolic here, or we want to describe the valence band, which is a little bit more complicated. But the thing is, we want to describe just a small range of the band structure and not the full band structure to get an effective model that captures the essential physics of the material. This is the purpose of K.P. So how do we get the K.P Hamiltonian? Very briefly, we start with the Schrödinger equation, and then we remember H is just the kinetic energy plus potential, but the potential is periodic because the crystal lattice is periodic. So this periodicity allows you to use Bloch's theorem that we see in solid-state physics, which tells us the wave function is periodic apart from a phase given by k dot r. And if you put this wave function back into the Schrödinger equation, the derivative here in the p operator is going to split this product into three terms: the k squared term, the p squared term, and the product term. And it looks like this. So the k dot p Hamiltonian has the kinetic energy, the potential, then what we call the trivial k squared term, and the k dot p term, which we're going to treat as a small perturbation. So this approach allows you to split the Hamiltonian into a dominant contribution that gives you the eigenenergies of the system, and a small perturbation that gives you the dispersion, how the energies depend on k. But to use this Hamiltonian, we have to go a little bit further and apply perturbation theory in the sense of the loading partitioning. So the idea is you have the Hamiltonian, I'm going to write as H0 plus a perturbation H prime. And let's assume that we know the solutions of H0, which in this diagram I show as these dots, this green and red dots. Assume these are the known solutions of H0 at the gamma point or at some other k point. And then we want to split the solutions into two sets. You have set A and set B. So set A represents the bands you want to describe with the k dot p model, and set B are all the other bands that we call remote bands. So before showing you the formal solution through this loading partitioning, let me first do a back of the envelope idea of what I mean by splitting the equation into set A and set B. So this is just like an overall idea of what happens. So you take the Hamiltonian and you project this Hamiltonian into the subspace of set A and set B. Like a back of the envelope idea, let's write down like this. So you have in the diagonal, you have the energies. Out of the diagonal, you have the couplings. I'm going to keep calling H prime for simplicity here. Then what we can do is we can write the two sets of equation, multiplying the first line by this column, the second line by this column. So the first line of the equations give us this, and the second line of these equations give us this. So these are coupled equations for subset A and B, and we want to decouple these equations. So to decouple, we can take the second equation, for instance, and put B explicitly to the left and write in terms of A, of the A eigenstate, and then you put this B eigenstate back into the first equation. And what we get is an equation for the A subspace, but the Hamiltonian changes. It takes this form, and that's more or less what we're going to call the effective Hamiltonian. The experts in the audience might know that I'm forgetting about something here. This is just a back of the envelope idea of how the decoupling happens. If you do this properly and do the renormalization of the wave function, or if you do the actual loading partitioning approach, then you get something slightly different that looks like this. It's the same idea, but this is a explicit expression for the matrix elements. So HMN is the matrix element of the Hamiltonian between the eigenstates M and N, and these eigenstates belong to set A, which are the bands that we want to describe. And it looks like this. So you have a zero order term, which is just the eigenenergies, and a trivial k squared term. You have a first order term, and pay attention here now, because this is the important part. So the first order term has k dots, a matrix element of the pi operator, and the pi operator is just the p operator with a spin orbit coupling correction. So this is the first order contribution. And then you have the second order contribution through perturbation theory, which has this k dot pi matrix element twice. So it's a square term and some energy denominators, and it goes on. You have third order, fourth order, and so on. Instead of doing the loading expansion, there's a recent alternative, which is called pMa-block, which is a code developed by the Delft group, which does this uncoupling in a different fashion. It's different than loading partitioning, and numerically is much more efficient, and we want to incorporate this in the next version of the code to make it faster as well. Okay, so the point is, let me go back just here for a second. So this effective Hamiltonian in this explicit form depends on these matrix elements, which are related to what I'm calling here P and VF, or the Kane parameters. To make it more explicit, for instance, if you want to model the band structure of gallium arsenide, which has that parabolic conduction band and the valence band down below here, if you do group theory analysis and K.P analysis, you're going to see that your Hamiltonian looks like this, just the upper triangle here. So you have the eigenenergies in the diagonal, and out of the diagonal you have this KXP, KYP, KZP, and this capital P here are the Kane parameters that define your material. So you need numbers. I need a number for this P parameter in order to be able to calculate the band structure. And the same happens for graphene. So the effective model for graphene looks like this, is the famous sigma.k Hamiltonian. But it depends on the prefactor, which is the Fermi velocity. So group theory and K.P theory give us these forms, these shapes of the Hamiltonian, give us this overall structure for the Hamiltonian, but they cannot give us the number for the parameters because these numbers are material dependent. So that's where the code enters. So the idea of the code is to calculate the value for the P parameters instead of fitting the DFT data. We want to avoid fitting. We want to actually calculate the parameters from ab-initio simulations. Okay. So with that, I'm gonna move to the DFT code itself, the DFT2kp code itself, just to tell you how it works, and then I'll go through examples before showing you the code itself. Okay. So the overall structure goes more or less like this. So we know that the Hamiltonian takes this explicit form in terms of the matrix elements, and what we want is to calculate the matrix elements. So what do? We have a patch for Quantum ESPRESSO, so we made a modification to the Quantum ESPRESSO code, and you have to compile Quantum ESPRESSO with our patch, with our modifications. And what this modification do is, when you run Quantum ESPRESSO as you usually run it, you do the PWX self-consistent and non-self-consistent calculation, and then you do the bands.x calculation to get the bands. And what we have modified here, we have modified the bands.x calculation to properly calculate all the matrix elements that we want. So Quantum ESPRESSO calculates the matrix elements for us. Also, Quantum ESPRESSO gives us the eigenenergies, of course, which is just the band edges from the DFT simulation. So then we move to our code, and what the code does is it reads the Quantum ESPRESSO data, the energies, the wave functions, and those matrix elements. Then the user selects what is the set A, what is the list of bands that he wants to describe via a K.P model. This is up to the user always. And the code develops what I call an automatic ugly model. And what I mean by ugly will be clear later. You could stop here if you are okay with the ugly model. The code is fully automatic up to this point. But if you want to move from an ugly representation to an optimal representation, you have to do a change of basis. And this change of basis depends on a choice by the user, and this choice requires that the user knows a lot of group theory. Okay? So it's automatic up to here. From here on, a group theory is necessary. Okay. So for you to understand what I mean by this change of basis, let me use graphene as an example. So graphene, this is the band structure from DFT of graphene, and the direct cone is right here. So if I run the model automatically, without caring about Hamiltonian being ugly or beautiful, I get this band structure in these red lines, which describes the direct cone quite well near this green area here, which is the region that we want to describe the effective model anyway. There's some discrepancies here, but don't worry about this right now. What matters is the green zone here. Okay, the bands are okay, but how does the Hamiltonian looks like? So we want the Hamiltonian to have the sigma dot k structure. So h bar vf, sigma x kx, sigma y ky. We want it to look like this. But if I calculate the Hamiltonian straight from the quantum espresso basis, I get something like this. So I get this matrix on top that has nothing to do with sigma x, and this matrix on the bottom that has nothing to do with sigma y. So this is what I call the ugly model. It gives us the correct band structure. This model is correct, but it's ugly in the sense that it can always change the basis into something that is more appealing, that looks like this. And the trick is, how can we change the basis into something more appealing? So to do that, we need to know a little bit of group theory. I will not give a lecture on group theory here. I'm going to go quickly just to give an idea of how it works. So this is the lattice of graphene, is an hexagonal lattice, and this is the Brillouin zone in K space, in the reciprocal space. The symmetry group of graphene is generated by two operations, the C3Z, a threefold rotation around the Z direction, and a mirror around the X direction. These are the generators for the K point group, because the band structure of graphene are at the K point. So to describe this model, we need a basis function. So the basis function is going to be composed by A and B sublattice wave functions composed by pz orbitals in graphene. And they look more or less like this. So on each of these black dots, you can assume there's a pz orbital centered there, and the numbers here, or these phase factors here, are the block phase factors due to the translation between these two pz, or these three pz operators. So this structure is what I'm going to call the wave function A, or the basis function A, and this is the basis function B. It's very similar to A, but it's flipped. Okay. And again, the phase factors are just block phase factors due to the translation. So from this, I think it's more or less easy to visualize that the matrix representation for the C3 and the mirror X operator are these two. So for the C3, for instance, C3 rotates this triangle back into itself, but carries the phase around. The same here. It rotates the triangle back in itself, but carries the phase around. So the representation is diagonal because it leaves the triangle invariant, but it gets the phase because the phase moves around as you rotate. And the mirror X is easy to see that if you apply a mirror taking x to minus x, you take the A basis into the B basis, and the B basis back into the A basis. So mirror X takes this form of this sigma X matrix. On the matrix. Okay, so I'm going to call these representations the ideal representations, or the representations that I want Quantum ESPRESSO to use for the wave functions. And the reason why Quantum ESPRESSO doesn't use this basis automatic is because it's a numerical code that diagonalizes the Hamiltonian self-consistently through some iterative procedure. And whenever you have a pair of degenerate wave functions, any linear combination of these two wave functions remain a solution of this degenerate subspace. So you have some freedom to choose what is the linear combination, or what is the representation, or what is the proper basis where these two wave functions are represented. So ideally, we want this wave function to be represented in this fashion that takes this matrix representation. So I'm going to put it here. This is the same matrix representation, just putting the numbers to this phase factor. So it looks like this in the diagonal, and mirror X is pretty much the same as before. But I can calculate this matrix representation also using the wave functions from Quantum ESPRESSO. And they look like this. Again, it's, like say, an ugly representation. It's correct. It is the proper representation of the wave functions in Quantum ESPRESSO, but it has nothing to do with this, or it has something to do. They are equivalent representations up to unitary transformation. So the thing is, can we find a change of basis, a unitary transformation that takes this representation or this basis set, the Quantum ESPRESSO basis set, into our ideal basis set? And it turns out that we can find it. So in this case, it looks like this. So if you apply a unitary transformation to these matrices using this U matrix, you get exactly this ideal basis. To find this unitary transformation, this is a big part of the code is developed to find this U transformation. So what we want to do is we want to find U that transforms the DFT basis into the ideal basis for all symmetry generators of the crystal group. This is a quadratic equation for U, so what we do is we linearize by multiplying everything by U dagger, and we can solve this using singular value decomposition. If you want to know more about how I actually solve this equation, which is not so trivial to solve, I have extra slides in the end. You can ask me and I'll show you the extra slides. Okay? Otherwise, if you want to check later, it's well described in the paper as well. So what about the Hamiltonian? So this matrix U fixes the representation for the symmetry operators, and it was designed to do that. So what happens if I apply the same matrix operation to the Hamiltonian, that ugly Hamiltonian? So I apply it, and what I get is a Hamiltonian that matches what I want. So this HX matrix, which was had this ugly shape before, now looks like sigma X, and this one looks like sigma Y. And you can see that the prefactors are exactly the same, and they should be exactly H bar times VF. And if you check the numbers, you convert from Bohr units to electron volt nanometers, or if you extract the Fermi velocity, you get this value, which is exactly the value reported in the literature for the Fermi velocity in graphene. So it works quite well. Okay, so this is the transformation that requires a bit of group theory from the user to know what's happening. Before showing you the code itself, let me do an overview of examples of what we have been running. So we started with zinc blend because there's a bunch of papers showing results for this material. So this is for cadmium telluride. You have here the conduction and the valence band well described. Mercury telluride, again, the band inversion is well captured here, and the bands match well the DFT data. And gallium arsenide, again, conduction and valence bands well described. I can zoom in so you can see, focus it on the conduction and valence band. You can see that the red band, which is the model band, matches quite well the blue dots, which are the DFT calculation. It's a very good agreement, remembering that there is no fit involved here. The bands or the parameters are calculated straight from the DFT model. We also did the same for wurtzite materials, for instance, gallium potassium, GaP. It has a much more complicated band structure. You can see it's not a parabola, it has anisotropic dispersion here. The valence band is quite well described as well, including the anti-crossing that happens here in the valence band. Gallium nitride is a little bit more complicated. You can see that the conduction band doesn't match very well the model. What happens here is that in this calculation, what I'm showing here is the gallium nitride calculation using the p operator without spin-orbit coupling. But if I do the full gallium nitride calculation, including the spin-orbit contribution, you can see that the agreement is much better. And it's well known that nitrides require the spin-orbit coupling calculation to get proper band structures. And the agreement in the valence band is also improved when you include the spin-orbit coupling. Okay. Some other examples we have tried to run for perovskites. It matches quite well the bands near the low energy region. Rock salt materials. Here I'm doing a rock salt band structure using only 2 bands, and I get some reasonable agreement. But you can see that there are other bands very close by these two. So in principle, to get better results here, they should account for more bands. At least these two bands should be included in the model to increase the accuracy. And here's some results for molybdenum disulfide, the decalcagenide, and you can see that it captures well the effective mass of the band structure here, of the conduction band and the valence band as well. This material in particular is a bit challenging because it has a value here that cannot be captured by traditional K.P methods, because you can only get this parabolic dispersion here, it doesn't go back, okay? If you want to ask me about what are these black lines, I can explain later, but I'm gonna, for now, just give an overview, okay? And what we want for the next versions of DFT2kp, let's say DFT2kp 2.0. So the main goal is to get quantitative predictions. We want to go further and get realistic simulations that match experimental data. And in the next slides, I'm going to show you our first preliminary results for the G factor and how to fix the gap. Because a major issue to solve, to get quantitative predictions is to fix the gap. And the DFT experts in the audience know this is a major DFT issue. So to fix the gap, you can use hybrid functionals, meta-GAs, GW, but I'm not going to show you this today. I'm going to show you the scissor shift approximation, which is a trivial trick to fix the gap, just to show you that we can, fixing the gap can improve the results. For the next version, we also want to develop a VASP version and maybe a Vin2K version, but to develop this one, I need a license. So it depends on how it goes in the future. So let me focus now on gallium arsenide. I'm going to show you the results first, and once I finish showing you this, I'm going to change screens and go to the code so you can see it running. So I'm going to describe the conduction bands of gallium arsenide up to K cubic. So the Hamiltonian looks like this. You have the gap energy, which is pretty much the energy distance in here, between the valence and conduction band. You have the parabolic mass, and we want to focus on the value of the effective mass here. And you have the spin-orbit coupling, which is the Dresselhaus cubic spin-orbit coupling that depends on this parameter gamma. Additionally, you can consider the Zeeman effect. So the Zeeman Hamiltonian looks like this, and you get this G factor. So what I want to calculate here is the values for G, M, and gamma. The G factor calculation is done like this. So it's basically the matrix element, the diagonal matrix element of the angular momentum and the spin operators. Okay. So if I'm going to show you first results using the GGA functional, which is like the one we usually start when running DFT calculations, and I'm going to compare with the experimental parameters. So for the gap, the experimental gap should be close to 1.52 electron volts, and if you run DFT with GGA, you get 0.4, which is far off. So this issue with the gap in DFT is well known, but it propagates to everything else. If I check now the effective mass experimentally should be 0.067, but with GGA I get 0.030. Quite far, like half of this, right? For the Dresselhaus gamma parameter, experimentally it's in between 5 and 11 electron volts angstrom cubic. And if I run with GGE, I get 43, which is far off the experimental data. And even worse is the G factor. It should be minus 0.44, and GGA give us minus 10, which is really bad. But again, these three parameters are really bad because the gap is bad. So let's try to fix the gap. So to fix the gap, we want to do the scissor shift, and the scissor shift is just a trick, it's not a real calculation. I'm just going to take the DFT energies, and I'm going to manually increase the gap. I'm going to manually put all this band up, such that the gap goes to 1.52. But I'm doing it by hand. It's an approximation, just to see what happens, basically. And it works, or it goes in the right direction, because once you increase this gap, what you are doing is you are changing the denominators in that perturbation theory. And this affects all the matrix elements. So this is what I get. So if I fix the gap, so I force the gap to go from 0.4 to 1.52, and the mass grows from 30 to 96. Okay, maybe a bit too much, but it grew. It went. It was too small. It grew. Maybe it grew too much, but it went in the right direction. The Dresselhaus coupling went from 43 to 5.6. Okay, it's very close to the acceptable range in the experimental data. Today, the experimental values for this parameter are closer to 9 electron volts angstroms cubic, but it's in between this range is acceptable. And the G factor went from -10 to plus 0.40 by doing this scissor shift. Okay, it's wrong because it has the wrong sign, but again, at least it's in the correct order of magnitude. Okay. To have a more clear picture of what's happening here, I plot both the G factor in blue and the effective mass in orange as a function of the band gap. So I'm opening up this band gap, changing the value by hand, and I calculate the G factor and the effective mass as I change this gap by hand. And the G factor goes there from -10 all the way to 0.44. And in the process, it goes through the correct value, which is -0.44. And the same happens for the effective mass. So the effective mass goes from -0.03 and it grows up to 0.09, but it crosses the correct value of 0.067 here. But they don't cross at the same band gap. The correct band gap should be up here, okay? So the scissor shift help us go into the right direction. It moved us from here up here, but it went too far, okay? But it's a very rude approximation anyway. So to get better accuracy to compare with experiments, we have to fix the gap. And to prove to you that this is not just an issue in our code, I selected some papers here from 2010 from George Kresse and Blaha's group. These are very important names in the DFT community. So they calculate the effective mass for gallium arsenide, and as you can see, they get the values 30 and the values 90, which is pretty much the same values that we got here and here, depending on the functional they use. They managed to get the 0.66, but there's some tricks hidden here to get there. Some other papers, again from Peter Blaha, more recent one from 2021, again for gallium arsenide, they still get 0.030 and 0.90. So to fix the mass is quite complicated. Fixing the gap nowadays, people know how to do in DFT, but fixing the gap and fixing the mass requires a little bit more work. Another work that is important from Dimitra and Fabian in 2016, they calculate the spin-orbit couplings. In particular, they calculate gamma, the Dresselhaus cubic, and as you can see, they managed to get something very close to experimental data, 9.13 electron volts angstrom cubic, or with GW calculation, 8.5. But to get this, they had to use this meta-GGA, or the GW formalism, to fix the gap and correct the band structure, which is what we're going to do next. Okay? So the idea is to improve the results, we need to fix the gap. Or even worse, we have to fix the gap and fix the dispersion, fix the effective mass. So PBE, GGA fails in both. It gives the wrong gap and the wrong mass. The scissor shift approximation fixes the gap, but not the mass. And it's under investigation now, what we're going to do in the next version of the code to try to fix this. So the idea is, let's try other functionals norm conserving, ultra soft, PAW, PBE, PBE-SOL, to see how they handle these quantities. I want to run method GA, the modified Beck-Johnson method GA, but this one is available only in VASP and Vim2k, so I need to develop the code for VASP in order to use this method GA. Hybrids, HSE, I'm already doing this. I don't have preliminary results to show right now, but this is under current development. I'm running some materials with hybrids, and I can tell you that it helps, but it's still not conclusive. G0, W0, okay, it's interesting, but I'm guessing that it's going to give similar results to the scissor shift, because G0, W0 fixes the energies, but doesn't fix the matrix elements. So I'm not sure it's going to help much. And the full GW, okay, maybe, but then the experts in the audience know it takes time. It's a very complicated code to run. Okay, and how to use the code now? Okay, so in the last minutes of this talk, I want to switch to the code and show you a little bit about how we run the code itself. And as I'm announcing here that in November, pretty much after the classes end here in Uberlândia, I'm gonna record some video tutorials explaining all the steps on how to run the code, how to compile Quantum ESPRESSO with our patch, and how to run both Quantum ESPRESSO and how to run our code to get the results. So I'm gonna give you a sneak preview of this tutorial by showing you some details right now. Okay, let me switch here to the code. Here. So I'm going to use gallium arsenide as the main example here. So this is the input files for gallium arsenide. This is just traditional Quantum ESPRESSO input files for the experts. So I'm going to do the self-consistent calculation with norm-conserving functionals. Gallium arsenide, eBrav2, the lattice parameter, the convergence parameters here. I'm going to do it with spin-orbit coupling, the list of atomic species here, and the functionals that I'm using, fully relativistic PBE functionals, the positions, and the number of K points. This is exactly the same input file we would get for any Quantum ESPRESSO tutorial. You run this with Quantum ESPRESSO, and then you move and you run the non-self-consistent calculation to get the bands. And the only thing that changes is that you're going to do the calculation now over a K path, just to plot the bands. So here I'm going from points L to gamma to K. Again, this input file is exactly the same from any Quantum ESPRESSO example. The one that changes is the bands calculation, the one that extracts the eigenenergies to calculate the band structure, to plot the band structure. So in the beginning, everything is the same as all these parameters here are the same as in the Quantum ESPRESSO documentation. What changes are these last ones here. So what I'm saying here, this parameter LP equal true tells us that we want to calculate the matrix elements of the momentum, that we want to calculate the band structure. And this tells us that we want to calculate all the matrix elements of the momentum, because the original Quantum ESPRESSO code does not calculate all. So this is my modification on the code, that now it runs and calculates the matrix, all the matrix elements, and saves the data the way I need it. And it's going to save the data in the file k.pdat. And it's going to focus on the 31st K point. And why 31st? Because the 31st K point is the gamma point that I selected here in the non-self-consistent calculation. So this is the only difference from usual Quantum ESPRESSO calculations that are going to run. So this creates a series of files. So the output files are all here. And the new file is this k.pdat, but it's I cannot open it here, it's very large, okay? Okay, so having all these files, I can go to the Python code that reads this data and develops the model. So I just import my library, NumPy, matplotlib, traditional libraries. So this is the DFT2kp library here. And the first step is to read the data. So the first command here just tells the code where the DFT data is stored, which k point is going to be used, and the name of the k point is gamma. So for gamma, you have to use gm. For k, just letter k, and so on. Okay. The second command is to read the k.p data, the k.p data. I run separately for particular reasons that I don't want to discuss here in this overview. Okay, but basically you can read the DFT data as well here. And I have some auxiliary data here, some vectors that help us do the plot. So in here I just put the numbers and the labels for the k path, and I extract this again from this file here. So L gamma k, third points in each direction, and that's what I'm forming here, L gamma k, third points in each direction. And I read the bands data from DFT as well. It has a structure to help plotting. Now, for some important aspects of the code, the next step is you have to select which is the range, which are the bands that you want to model. So I'm putting here 3 examples. So if I want to model the conduction band of gallium arsenide, it's given by the bands 28 and 29. Third doesn't count. 28 and 29. To check this, you can open the band structure with X and Grace and count the bands and check the index of the bands there. So it's the 28 and 29, for instance, in this case. Okay. To make sure that you are selecting the correct band, our code plots the band structure. Let me show you here. I'm just going to run it. So I'm plotting here the DFT bands in blue, and the bands you have selected are marked in red. So again, so this is correct. I'm selecting the conduction band. If I want to use the valence band, I can just comment this line, and I can model the valence band, which go from 22 to 27. So now the code marks here the valence bands for you to check. Or if I want to run and make a model for both valence and conduction bands, I go from bands 22 to 30, and it marks here that I'm going to model all these bands. Well, to start this overview, let me start with just the conduction band. So I want to model the conduction band, 28 and 29. I pass this command here, the define set A, which is going to tell the code what is the set of bands you want to model, and to which order of k.p you want to model. So here I'm going to do up to k squared. So this command here will already develop the ugly model for us. Okay, we're going to do the fold down, the loading, partitioning, and do the ugly model. So, okay, again, I'm choosing only these bands, and this section of the code helps you plot this band. So this command here builds the Hamiltonian and gives you the ugly Hamiltonian here. And this command basically uses NumPy to calculate the eigenvalues as a function of k. Okay, so it's a very fast calculation, and I can plot the results. And as you can see, the conduction band has this parabolic shape, and it has more or less the correct effective mass. Okay, all these examples are shown in the code if you want to check more details later. Okay, if I want to improve this code, I can go back here, and instead of using just the conduction band, let's model the full sets. The conduction and valence bands, the 8x8 model. So I'm going to model all these bands together. I'm going to run here the Hamiltonian. It's very quickly, and then I plot the results. So again, here now I have a much better model. It captures much better the conduction band, and capture as well the valence band. If I want to improve further, I can include more bands to the model just by selecting a larger set A of bands of interest. That takes practice to understand how many bands you need, but it's very easy to change the number of bands that you want to model. But again, this is the ugly model. If I want to go for the optimal model, I need to know a bit of group theory. And what we do is I use this QSym packet from the Delft group to do the group theory analysis here together with my code. This is something that I want to improve in the next version to make this process more automatic for the user. Okay, so I'm going to do here the model for conduction band. So conduction band, the basis is spin up and spin down. So all I need is the exponential that represents the rotation of spin operators, which is coded here for the experts. And then I have to describe this matrix for the C3 operation, which is a threefold operation around the one-on-one direction, and the S4 improper rotation around 001. So the QSym code help us develop these representations, and we include time reversal symmetry. And if we run, we get this effective Hamiltonian. This is the structure that QSym from Delft group give us. And if you want to interpret this, you have to get some pen and paper to understand a little bit better. But this Hamiltonian is exactly the same I was showing you before. So C0 in the diagonal is the gap. The k² term here, you can see kx, ky, and kz square is this C1. So C1 is h bar over 2n. And this C2 terms on the diagonal and out of the diagonal is essentially the gamma parameter, which I show here in more details. So then the code, you can run the code to find these coefficients. So you have to to calculate the matrix representations, add time reversal because Quantum ESPRESSO doesn't account for time reversal. And then you run the code to find that matrix U and change the basis from the ugly basis to the optimal basis, and it prints the results like this. It prints the values for the coefficients, again here, C0, C1, and C2. So now you have the values in both units, in Bohr units and in electron volt nanometer units here. So from these values, then it's easy to understand. As I said before, C0 is just the gap, 0.4. It's wrong, should be 1.5, but it's a DFT issue. The effective mass is just 1 over C1. So C1 is 0.33, 1 over C1 is 0.030. And C2 is the gamma, which gives us 4.3 electron volt angstrom cubic. So in the end, it's very easy to run the code, but again, just to emphasize, the first part of this tutorial is online on the repository if you want to check later. The first part builds the ugly model that we don't even show here on the screen, but gives you the correct bands down here, sorry, gives you the correct band structure. So if all you care is, if you don't care if the model is ugly or beautiful, you can stop here. If you want to see the code, the Hamiltonian, it's stored in a dictionary inside the k.p class. And you can see all the matrices in here. The zoom is a bit too big. If you want to see, for instance, the k² matrix, it's going to be a bunch of terms, but it looks like this. It's going to be this is the ugly model, but it gives you the correct bands. And if you want to do the optimal model, then you need to know a little bit more of group theory, and use QSym and these optimal representations to get the proper shape of the Hamiltonian that you want. Okay? Let me go back to the presentation. So, just as a reminder, what I show you here was just an overview of how the code works. All the examples are on the repository. You can check in much more detail. You can contact me at any time if you have questions, if you want help using the code I'm open. I'm helping a Chinese team to run the code. I'm helping my former student Renan to use the code. Some other people are emailing me asking about details on how to do this and that. So feel free to ask me anything. I'll help you. And I promise that in the next version, I'm trying to make everything more and more automatic and easier for the user to use. And a final reminder, still this year, November, I'll start recording in November, but up to December, I'll have a tutorial with everything that I show you here in much more details, with proper slides, showing step by step on how to run the code and why we do this and why we do that. So a series of videos explaining all the steps will be available in November if you want to check later. It's going to be on my channel, so you can follow this link later, okay? So with that, I'd like to thank my research group and our colleagues at UFO. So I'm here, my research group is Subgenano, the web page is shown here. Brian's a PhD student, Pedro and Olavo master students, João, Felipe, and Denner are young undergrad students, and Vitor is a new student who will be in charge of helping me develop version 2. So I'm training currently Vitor to help me develop all these new features that I want to have on version 2.0, and the other members will sure help along on the way on smaller tasks. Okay, I have here a list of things I want to change for the version 2.0. So automatize the method to find the ideal representation, at least to give my choice of ideal representation, but I'm going to still allow the experts to change the representation to whatever they want. G-factor calculation, new versions for other DFT codes, initially VASP, but maybe Vin2k and others. I want to replace the loading partitioning with pMyBlock, which is much faster from the Delft group, and other improvements on the calculation of the matrix elements, improve the user interface and documentation and so on. And okay, with that, this is all I have to say, and thank you all for the attention.
Gerson, thank you very much for this very nice talk, and I should inform you that you broke all our audience records. We had a maximum of 50 people watching, so that was quite amazing. And so we are expecting a lot of questions because we have a large audience, so this is open to questions. So Emmanuel has raised his hand. He wants to ask a question.
Hi, Gerson, can you hear me?
Thanks.
Can you hear me?
Yes, it's okay. Go ahead.
Thank you for the talk. Just a simple question. It can be studied with magnetic materials. Is that some limitation in your code in this study, or you don't have limitations for that?
Yeah, I got an email about this earlier today from somebody else. Yeah, so yeah, we want to do magnetic materials. We didn't try. In principle, there is no limitation. You just have to try it. Okay.
Okay, thank you.
There is a question on the public chat here.
Chat, yeah.
Yeah. Diego is asking what is the difference between what I developed and pMyBlock. Okay. Yes and no. I cannot give you all the details, Diego, and I'll tell you why. Let me just move here to the equation. So what I have implemented is exactly this. Okay, I have exactly this summation for the second order. And if you go to Winkler's book in the appendix C, if I'm not wrong, you have the expression for the third order and the fourth order as well in terms of huge sums. So I was lazy. I actually implemented all the sums. It's quite huge, but it's there in the code. And it's very slow as well. It's not good. So pMyBlock was developed by the Delft group, I didn't study the paper in details. I saw some talks from their group, but I didn't study the paper itself. So it turns out that they were developing an alternative to the loading partitioning, to the fold down approach. And in the process, originally they were going to implement an efficient method to do the loading expansion. But throughout the calculation, they actually found out a better approach to do the folding down, which is somehow different from the loading partitioning. But I cannot give you details because I didn't study the theory, the new theory that they have developed. There's an archive paper, I think, yeah, here it is. This archive paper gives you the theory of what is different in that approach. But I cannot give you much more details than that, okay?
Hannah has raised his hand. Right now, you can ask the question.
Can you hear me?
Yes.
Yep.
Great. So thanks again for, George has already said, but thanks again for a very nice presentation. I have a very simple question, and it is about the second part of how you construct the Hamiltonian, because you said about the ugly part and the beautiful part, right? Mm-hmm. So if, how does the code works if the only symmetry you have in your system is the identity?
Yeah, then all you have is the ugly code. Okay. If you don't have symmetries to help you find the beautiful model, then there's nothing you can do. You can only have the.
Yes, I get that, but in terms of it doesn't affect your effective model, right? So this red color that you're showing in your picture, for example, it will not.
Okay, let's break it down a bit. There is two things. There is the effective model, and that is the band dispersion. Okay, so the difference between the ugly model and the beautiful model is a change of basis. It's a unitary transformation. So unitary transformation don't change the dispersions. Okay? So the red lines here, the band dispersions, will be exactly the same whether you are in the ugly model or on the beautiful model. We want the beautiful model only because, let me go further here, only because we want something that makes sense. We want to write the Hamiltonian in a basis that first is easy to remember. I mean, nobody would publish a paper with a Hamiltonian written like this. It's difficult to read. What does this number mean? They don't mean anything. But this number means something. This number is the Fermi velocity. So you want to write your Hamiltonian in a form that has meaning. And to have meaning, you have to change basis into a basis that gives you the Hamiltonian with a shape that recognize what the parameters mean. Okay, but it's a unitary transformation, and unitary transformation don't change the dispersion. So if you want to take, for instance, if you want to take the model, the ugly model, and copy the data to run on Quant, for instance. Quant allows you to do transport calculations. You can do that with the ugly model. It doesn't matter. Okay, you're gonna get the same transport coefficients as you would get from the ideal model. It's the same. But to visualize, to interpret what the parameters are, you need to go to the ideal basis.
Okay, thanks. There is just one more quick question. Do you have you showed a lot of what you're planning to do next. I'm wondering if you're also planning to implement your code together with Quant, for example, because it would be very handy.
Yeah, actually, I think I forgot to put it here, but yes, a Quant interface is also something I want to plan. In practice, it's already there. It's implied in the background of the codes. If you check the code itself, not just the interface, it's kind of already there, but it's hidden. But yes, I want to do that. This is part of. It's more a feature of improving the documentation than changing the code, because you can move from our code to Quant very easily using that dictionary that I was showing you before, but I only show it quickly. In the tutorial, I'm going to show more detail.
Let's see. Thanks.
Okay, thank you, Helen.
Any more questions? Sergio, go ahead, please.
Hey, Gerson, thank you for a nice talk. So you said somebody should ask about the black lines. So here I am. What are the black lines?
Thank you. George, just so I don't forget, there are more questions in the chat.
Yeah, I am following here, yeah.
Let me go to something easy to understand. Okay. So whenever when I run the code, I can select how many bands I want to model, right? So in here, for instance, for gallium arsenide, I'm doing the model for, in red, is the model for 8 bands, okay? Traditional Kane model for 8 bands. But in the beginning of the talk, I was showing you some highlights of some papers that do 30 band models, 50 band models, and so on. So what I have in black is a K.P model with 1,000 bands, automatic. And it's quite interesting because it captures much more, right? It's 1,000 bands K.P model. Does it make any sense? Probably not, but I plotted to check how it goes, okay?
Wow.
But it's interesting because if you check molybdenum disulfide, 4-band model for molybdenum disulfide only gives you the parabola, but a 1,000 band model gives you almost gives you this side valley here. So it's interesting to see that you start to gain something that is closer and closer to a full zone K.P if you increase the number of bands.
So, and well, a corollary of that, Gerson, is, does it, including more bands, change the curvature, for example, or the Dresselhaus? I mean, in a significant way, when you're trying to fine tune, right?
Yes, not much. I'll show you why with another file here. I'll take gallium arsenide just because it's already here. Okay, so this is the full code for gallium arsenide. So it's pretty much the same. I'm gonna go to the end. Okay, so I can choose the set A. You do the model. So this is the coefficients for the 8x8 model. So it prints out all the coefficients here. Then you can plot the bands, and down below, in every single example that I have in the repository, you can check at the end the convergence. So let me just reduce a little bit the size of the font. Okay. So what I'm plotting here is the values for the coefficients C0, C1, C2 as I increase the number of bands. This is in log scale. So 10 bands, 100 bands, 1,000 bands. And you can see the convergence. So I didn't try anything above 1,000 bands. So typically, when you get to 1,000, it's converged already. It doesn't change much anymore.
Sure.
Okay. Just to take the chance here, there's one more thing that I forgot to say. I have a folder in the repository where I keep effective models, predefined models for traditional materials. So let me open here for Vertsite. So if you want to do a Vertsite calculation, you don't have to worry about group theory because I did the dirty work for you already. So I have it saved here, a 10-band model for Vertsite materials with all the representations already written down. And this is the 10-band model for Vertsite material.
Very nice.
Done. Just you can use this straight from the code. And if you want to do a 8-band model, which is more traditional than the 10-band model, it's already written down here. You can reuse it. Okay. So here on the gallium arsenide example, for instance, I don't have to do the group theory calculation. I just have a section here, a little bit above, where I read the predefined model and I move from there. Okay.
Oh, very nice. So going back to the convergence issue, so you could also imagine, of course, using different pseudopotentials, say.
Yes.
And
Yes.
so how sensitive is, the effective mass, especially, or I mean the G factor for that matter, but the Dresselhaus, your gamma, right?
Yes.
So how sensitive is that on pseudopotentials? I have no idea.
I can tell you that I've run with PB and the hybrids and HSC. Okay.
Mm-hmm.
And for the hybrids, I got it's here. For the hybrid, I got 0. I got 5. Should be around the correct value should be between 8 and 11. Okay.
Right.
So I got 5. So it improved a lot. Okay. It went from 43 with GGA to
Mm-hmm.
HSC. So it's quite sensitive. It changes a lot, and it's all connected. If you fix the mass, you fix the G factor and you fix the cubic Dresselhaus as well.
Mm-hmm. Mm-hmm.
Because they all depend on the same matrix elements in the end.
Yeah. Okay, very nice. So we'll one of the students here is interested in your code and he started playing with it. So we might be calling you about help.
Great. Yes. Whenever you want, just call me. I'll help.
Sure. All right. Thank you very much. Bye, guys.
We have some questions in the chat, starting there with Ernesto Caetano. What experimental pattern was used?
I think there's one before from Ramiro. My questions. Ramiro Marcelo, my question is about the key code. Is it possible to access the density matrix of the code? What do you mean the density matrix? The density, or the density matrix in the sense of the operator? I don't know exactly what you mean. If you can write down later.
I think Ernesto is not there anymore.
Okay.
No, he is. No, he is. Ernesto. No, Ramiro, right? Is the one
Ramiro. So Ramiro, if you want to.
Ramiro.
I'm not sure. I'll move to the other one, then I go back to Ramiro later. So Ernesto is asking what experimental pattern was used. Thank you very much. Okay. What experimental pattern? I also don't know exactly what they mean. If you want to.
There is someone asking for the title of the Winkler's book.
Okay. I usually call it the Winkler's book.
It's
show you.
Interaction, something, right?
Yeah, something. Give me 1 second. It's here. Spin-orbit coupling effects in two-dimensional electron and hole systems. Okay.
Are you going back to Ramiro's question?
Sorry.
The density matrix.
I don't know what he means by density matrix, to be honest. You can access the density, the electron density. You have access to that, but I don't know what is the density matrix.
Okay.
Because if you don't work with density matrix in the sense of the operator density matrix.
I have a couple of questions. You showed the very good agreement between DFT and the KP bands with 1,000 bands. I don't know how this changes as you go up in the number of bands, but did you have the curiosity of checking your bands, the KP bands with 1,000 bands, and the tight binding bands obtained by The
yeah.
traditional, Vanier 90.
Yeah, no, I didn't compare. No, the Vanier does a very good job fitting the bands throughout the brittle zone. Okay.
Because it's a fitting, right?
Okay. I had some discussions about that. Yeah, no, it's not a fitting. They calculate, but it's. I don't like Vanier 90 very much because the tight binding model they usually give in the end is very heavy. It has a lot of couplings and it's usually quite complicated to use. So I don't like to use it very much. And also, if you want to calculate the G factor, for instance, the G factor requires you. This is the expression for the angular momentum, which enters the G factor calculation, and this is given explicitly as a sum of these matrix elements. So to calculate the G factor via Vanier, I'm not sure if it is a good approach. So K.P is a whole different set of calculations that you can do, right? So they complement each other in a way. So you want to do tight binding whenever you want to do some numerics for transport calculations and so on very large systems with atomistic resolution. And K.P allows you to do analytical calculations or allows you to do much larger systems like heterostructures and quantum dots much more easily than tight binding. So there are two different approaches with similar aspects. So I didn't do a comparison between the bands, but well, that's my answer. Okay.
Okay. So Hannah wants to ask a question.
Yes, I have just one question / comment, because yeah, you're right. When we are using Vanierization and we have Vanier 90, it's sometimes a little bit tricky and complicated, especially when we want to transform it to a tight binding model, for example. But something that is really interesting when we are using Vanier 90 is that we can afterward, as a post-processing tool, use Vanier tools and, for example, project a band from a slab to the two-dimensional material, for example, in one-dimensional material. And this is quite handy because when we are doing a DFT, for example, for nanoribbon, it's very heavy. So is it possible, or do you also plan to go into this direction to take the Hamiltonian that you can construct and then project into?
Sorry. Okay, so within K.P, this is well known. You just for instance you have a Hamiltonian for graphene, for instance, sigma.k. So you have Kx and Ky, right? So Kx and Ky within the K.P model original, they are just numbers. They are values that you put the Hamiltonian and you change numbers to plot the band structure. But if you want to do a stripe, technically what you have to do is you replace the K with the derivative operator. And then you get a finite system. Then you can do a finite system. Just have to transform the K into a proper operator. If you do this for graphene, you're going to have a problem. There's going to be the fermion doubling problem. There's a paper from our group that deals with exactly this issue. But if you do for other materials that don't have the fermion doubling problem, it's just a matter of replacing K with the derivative. Okay?
Okay. But this is not part of the code now, right? So
no, this is not for the user. No, it's not part of the code because then it's up to the user. This is I don't think it would be part of the code. But that maybe the interface to quant kind of already does this, because the interface to quant will basically discretize this momentum into a lattice, into a derivative, into a lattice, and then you can do whatever shape you want. So it's kind of already there.
Yeah, thanks. Thank you.
Thank you. Okay.
Any more questions, anyone? Apparently not. So if not, let's thank the speaker again. Thank you very much, Gerson. I will be contacting you to get the slides and post them together with the videos in our YouTube channel.
Sure.
Okay. So thank you very much, and see you around.
Thanks everybody for the audience, and see you guys around. Goodbye.
Okay. Bye.